Hi, David from Electric Teaching here, and I'd like to do another shell versus washer situation here. Make it slightly harder than my last videos on shell versus washer. I'm going to use the function and the area bounded by these functions, 2 root x and 2 times x, the line 2x. And we're going to rotate it this time about a vertical line, x equal 2. The last one I did was about a horizontal line. So this one should be a little bit trickier than the ones before, and I'd like again to test how shell looks versus washer. So to do this one, I think I'm going to use my Python grapher that I've made, and I have a video sequence to show you how to make one of these if you're interested in programming and maybe having a personal little grapher like this one. And this one does integration for me too, especially with area between curves or bounded by curves. So the first graph I'd like to look at it is 2 square root of x. I'm going to graph this one. Oh, I need to do that again. Sorry, 2. I got to do this carefully here. Let me try that again. 2 times the square root. I got to do times. I'm used to working on the TI-83. So 2, have to do the times symbol, shift 8. Square root of x, and there's that graph. I'm going to add a new graph here. I'm going to do 2 times x. This little graphing program can do integration. I'm going to select I here to evaluate. I've programmed this in. And I'm going to integrate between the bounded area. It looks like it's bounded by 0 to 1 xy. So I'm going to integrate from 0 to 1, and it's going to fill in the area. And it's going to tell me I've got a little approximation of what that area is, and it looks like it might be approaching about 1/3. But that's not what we're looking at right now. We want to spin this around x equal 2 line. We want to spin that around x equal 2 line and create a volume. So I'm going to take a snippet of this thing real quick and bring it back into my graphing utility here. Or excuse me, not my graphing utility, my note-taking area here. And let me enlarge this just a bit here so we can play around and get a better visual on it. So let's rotate this about x equal, what did we say? X equal 2 line. So about the x equal 2 line. Here is x equal 2. And what we want to do is whenever you're doing a rotation, you want to take a look at the symmetry of the object on the other side of your rotation line to help you draw this in. So I'm going to try to draw the symmetry of this object, the mirror reflection, over on the other side of the rotation line to get an idea of what this looks like. It's always good to have a visual when you're trying to identify your radius. I think it's almost necessary here. So let's now draw in some circles to take a look at what this looks like. If I rotated it about this line, this object would spin around and create these circles, which I'm going to draw as ellipticals, as ellipse in the sense that we are looking at a 3D object from a perspective. So I'm going to be looking from the top view here, so this is solid, and then underneath I would see the front end of this inside, or excuse me, I wouldn't really see this inside at all. This would technically be all inside, and I should be drawing it like dashed completely. So when you draw isometric drawings of hidden sides, you always want to draw it dash. So there's this inside hollow part that's being controlled by the line. The radius of each one of these circles is being controlled by this line. That's good to see that. There's an outside circle, and we would actually see this part of the front of the outside circle. And again, it would be hidden and invisible back behind it. And this outside circles, let's draw another one here. The outside circles, okay, a couple things you want to notice about all of these things is that they're being controlled, the radius is being controlled by, this time, the radical curve, the 2 root x curve. And each one of these has a thickness. These are washers with a thickness. If I was to draw this in with a thickness, the thickness would be vertical, which is a dy thickness. And that's really important because we're going to use integration. Integration is summing up infinite items. In this case, we're going to be summing up infinite areas of this washer that's created. The washer that's created has an outside ring and a varying inside ring as well. And these will always be changing its size. And so what we're doing is we're getting this area stacked up from the bottom to the top And each one of these has a thickness of dy. So if you think area, outside area minus inside area, outside circle minus inside circle, that's where the formula for this came out. It's integral of pi capital R squared minus pi little r squared. In this case, we're going to be doing it in a dy fashion. You always want to identify your r's first. So my big R, which is right here, my big radius, really wants to be the whole entire length of 2. Really wants to be this whole entire length of 2. Let me draw one right about here. So if I draw it right here, it really wants to go and be the whole length of 2, but it's minusing this square root graph's x coordinate. This right here is the x length, or the x coordinate on that graph. So the big radius is equal to 2 minus an x length based on the square root graph. Well, since y equals 2 root x, y equals 2 root x for that function, then x equals, solving for it real quick, divide and squaring equals y squared over 4. You got to square both the y and divide by 2, so square the 2 as well. So that means the outside radius is really always controlled by 2, I didn't need the extra r there, is always 2 minus the y squared over 4. It's always 2 minus the y squared over 4. The little radius also has the same kind of feature. The little radius is being controlled by the linear. It really wants to be the whole 2 line, but we need to subtract off this little, right here, another x coordinate, but the x based off of the line y equals 2x. So in that case, to get it in terms of y, since our delta, our stacking of washers is in delta y, we need to solve real quick for 4x, and then get y over 2, divide by 2 on both sides. So now the same idea that we're going to have a radius, the little r, is 2 minus an x coordinate, which is 2 minus the y over 2. So we have our big R, we have our little r. Let's go back and take the derivative now. The integral now. So if we take the integral, we can factor the pi out. Most formulas have the pi already factored out for you. We're going to integrate in the dy of a capital R squared, and our capital R is 2 minus y squared over 4, quantity squared, and then we're going to subtract off the little r squared, that's 2 minus y over 2, quantity squared, and this is dy, and since this is dy, I need to analyze from what y? The bottom y to the top y. So it looks like we're going from 0 to 2, and I always want to check my radius. I always want to check. You should always want to check the radius in each situation, So if I put in 0, for y right here, the radius of at y equals 0 should be, for both of these radius, should be 2. See this unit of 2. So if I put in 0, 2 minus 0 is 2, and in this one, 2 minus 0 is 2. And if I check it at 2, both radius should be 1. You can see there's a little 1 radius there at the top. So if I put in a 2 here, it's 2 minus 4 over 4, so that's 1. And this is 2 minus 2 over 2, so that's also 1. So I feel very confident about this integral before even diving into the algebra. Too many times I've seen students not check to make sure it makes sense, and they end up spending a lot of time doing algebra for no reason at all. So let's go ahead and clean this up. We've got, let's see, a pi on the outside. I'm going to clean up the integration just a little bit more before we actually take the integration. I'm going to square out both these terms. Be careful of, make sure you think of foiling in a sense, or the shortcut to squaring it. So this is doubled and multiplied and doubled, which will then give me a minus y squared middle term. A plus y to the 4th over 16. Then I'll get minus, be careful of the minus, negative distribution will come into play here, so be very careful of that. 4 multiply and double, which will be 2y, which will be 2y. And then the last term will be positive there. Let's see, y squared over 4. And again, this is a dy. It's a dy. I need to check something real quick. Sorry about that. I just needed to check something real quick. And now let's collect some like terms. So let me scroll down and get myself a little more room here. Well, I'm not going to be able to. Let's see if I can squeeze this in. So we got pi on the outside. We need to clean this up still a little bit. So we're still running 0 to 2. If you look at this, this negative will be distributed. So that's a -4, which will cancel then with this 4. The negative gets distributed to there, and that's going to be a positive 2y, and there are no other y terms. So that's taking care of this one. You have a negative y squared and a negative y squared over 4. So that's negative, let's see, y squared and another quarter of y squared, so that's 5/4 y squared. And then, so that's those two. I just like to cross these off as I get to them. And then what's left is the positive y to the 4th over 16. I just wanted to make some more room here. Okay. And don't forget we got dy still. All right, let's go ahead and integrate now. So the integration, back to the integration now, is pi on the outside. We have integration of 2y, y squared, integration of 5/4 y squared. So the way I like to do it is open up a parenthesis for the multiplier that you're going to add in, or flip and multiply as I like to tell my students. Have the 5/4 still there. Change this to a y, add 1 will be cubed, so that means it's 1/3 down there. Plus, same idea, it's going to be, open it up, 1 over 16, y to the 5th, so this is 1 over 5. This is just a method I use to make sure I don't lose anything. 0 to 2 is what we're plugging and chugging. So pi on the outside, 4 for 2. The plug and chug of 0 is going to be 0 all the way across. So our answer is going to be basically what is the plug-in of 2, the substituting of y equal 2 and evaluating. If I put a 2 in here, this becomes 8. This becomes 8. So if this is an 8 right here, if this is an 8, then that's simply going to cancel that 8 and that 4. It's going to leave a 2 on top. So you're going to get negative 10/3 here. Negative 10/3. Next one is if I have a, 2 to the 5th is 32. Again, that's 32. Then the 32 and the 16 are going to cancel, and they're going to leave a 2. 32 and 16 cancel and leave a 2, and you got a 2/5 here, plus 2/5. Sorry, I do not like using a calculator if I don't have to. Common denominator there real quick. You know what? Let's go ahead and get the 4 plus 2/5 and then subtract off the 10/3. That'll be a little bit easier, and we'll be almost done here. 4, which is 20/5, so that's added with the 2/5, so that's 22/5. And then minus the 10/3. Let's get common denominator real quick. That's not too hard. Common denominator, let's make them 15. I'm going to multiply by 3, so that's 66 over 15. Multiply by 5 over here, that's 50 over 15. And now we've got our final answer. 66 minus 50 is 16/15 pi, and these are cubic units. Cubic units. So that's how I would use a washer method on this problem. I'm actually going to do the exact same problem with the shell method in part 2. I'm David from Electric Teaching. I hope that I have helped.